Welcome, everyone. We're delighted to wrap up during this session of the summer sprint that has been the Summer Scholars with a presentation and talk by one of our colleagues here at the Robotics Institute, Dr. Howie Choset. He is a pioneer in the field and a friend and an inspiration. I'd like to welcome members of the Summer Scholar team to do a formal introduction.
Hello, my name is Kaylee Barber. I am from Penn State and studying mechanical engineering and mechatronics in the Schreyer Honors College. This summer, as part of the Robotics Institute for Summer Scholars, or RISC program, I am working on origami compliant swimming robots. I am conducting research underneath a faculty member and along with 50 other scholars also doing research as well. On behalf of the RISC 2022 cohort, I would like to welcome you to this RoboLaunch session. I'd like to give my colleague Anna a chance to introduce herself as well. She'll be helping with facilitating question and answer.
Hello, my name is Ana Paula Garcia. I study biomedical engineering at Tec de Monterrey, and I'd like to welcome everyone joining us online on Zoom on YouTube session, and look forward to facilitating questions from you guys.
So whenever you have a question, if you're on Zoom or watching on YouTube, please just put it in the Q&A tab, and we'll be switching between those and in person. So it is my honor to introduce today's speaker, Dr. Howie Choset, Professor of Computer Science in the Robotics Institute and head of the Biorobotics Lab, where he works in areas including bio-inspired robotics, surgery, manufacturing, multi-agent planning, and robotic modularity. He's also worked to develop students' skills within the field of robotics, creating both an undergraduate robotics minor and fifth-year robotics master's program at CMU. He earned his degrees in computer science, business, and mechatronics, robotics and automation engineering from University of Pennsylvania, and his PhD in mechanical engineering and robotics from Caltech. Throughout his journey, he has also co-founded multiple robotics companies. Dr. Choset continues to have a major impact at CMU and beyond, and we're all excited to learn more about his experiences and research. Thank you for taking the time to speak with us today.
All right, well, thank you for giving me the opportunity to speak here. I have a couple of thoughts or emotions that run through my head. So there's gratitude. I'm so lucky to be able to talk with you people. It's also a little bit of guilt. I feel bad that I'm not there in person. I just have some juggling with family stuff I have to deal with. The other thing I also want to point out is, the awe that I'm in. This group of people, the 50 people that we have here, it's pretty great that you've gotten into this program, and good for you, or at least for those of you who made the most of the experience. It really, I hope, will change your life professionally in terms of what your interests are, or maybe just deciding what your interests aren't. I also hope that you make new friends that'll last forever as well. And this kind of opportunity, it's funny, a sign of getting old is when you say, well, when I was a kid, we didn't have that, but certainly when I was your age, something like, hell, even 10 years ago, something like this didn't exist. So I don't want to make you feel guilty, but you really are quite fortunate, and I really want you to appreciate what you have here as well. And for the most part, I think John Dolan's pretty great and deserves a lot of credit for this. But Rachel, she's the taskmaster here. You're not going to find anyone who has a depth of understanding of what it needs to educate in robotics, combined with just a sense of caring for all the people she encounters. And you're going to have Rachel for life as long as you keep in touch with her. And I really encourage all of you to do that because your careers are going to take lots of turns. You're going to college, maybe you'll get a job or go to grad school, maybe you'll volunteer, maybe you'll work for the government. I guess that's a job too. Please, I can't encourage you enough to, one, express your gratitude to Rachel, and two, keep in touch with her. It'll be in your best interest. The other thing I'm going to say is I prepared maybe a 20-minute, half-hour presentation, and I know we budgeted until 1, but I have this other call I have to take at 12:45, so I'm going to end a little bit early. If any of you has follow-on questions for what I'm talking about, I'm pretty easy to find, and there's my email address. So let's see. One of the things my group is famous for are these snake robots. And what's cool about these robots is that they can get into tightly packed spaces that people, machinery otherwise can't. And one of the uses is actually urban search and rescue. What you see there in the upper right corner is my student Julian sending the snake robot into a collapsed building in Mexico City. There was an earthquake in 2017, and we cleared some buildings at the invitation of the Mexican Red Cross. And what's nice about the robot is it can get to places that people and dogs otherwise can't access. And that's important when you want to locate victims as quickly as possible. What's also great about these robots is that they inspire a variety of interesting academic challenges. In other words, in order to make these robots work, it's not just engineering. Engineering, very important, and you want to get good at it, but it's also science. So it's both science and engineering. And I hardly want to say one's more important than the other, but it's that science that we figure out in the university. And that's why you go to a college professor or university environment to advanced snake robots. A recent project that we've been lucky enough to get a part of, and it's worth noting that, first let me tell you the project and I'll tell you how I got involved. So as you heard, I went to Caltech, and Caltech runs JPL for NASA. So technically JPL is not part of NASA, but it really is. And the Jet Propulsion Lab, they monitor all of our, I guess not our satellites, but our satellites that that NASA sends up and builds new satellites and such. And one of the things we're going to do is build a snake robot. It's called EELS. That's going to go to not to Saturn, but it's going to go to this moon. It's the closest moon to Titan. So I'm sure there are some space geeks out there, and they've all heard of the moon Titan, because Titan is one of the few moons that actually has its own atmosphere. It's also the largest moon of Saturn. But the moon that's closest to Saturn is called Enceladus, and Enceladus, it's the sixth largest moon. And what's unique about that moon is that it has the largest known ocean in the solar system. So maybe there are bigger oceans, but this one's bigger than anything we have on Earth. And this ocean actually, it almost covers the entire moon, the whole circumference, but it's still underground, so it's subterranean or sub-Enceladian. And in the south pole of this moon, there are these geysers. And we believe that the thickness of the rock or the ice is about 2 kilometers. So we're going to build a snake robot that's going to, be transported to this moon. It'll then get on the ground, crawl around, and then insert itself into one of the holes, snake its way down, and then swim inside of the moon. One cool anecdote is the way I got included on this project. It wasn't because of my Caltech experience, but I had hired a high school student to work in my lab one summer about 15 years ago. And that high school student, got into college, went to Carnegie Mellon, did all sorts of great things. And then that high school student eventually landed a job at JPL. And then he was the one who recruited me onto this team here. So I guess it paid off working with high school students. Of course, we're interested in making robots work underwater. And what you see there, we call it Hummers, hardened underwater modular robot snake, haha. And this robot it's probably tied for or the most maneuverable underwater robot in the world. And what's impressive is that we were able to build this robot for a fraction of the cost that our peers have. There's 2 others like it, one in Japan, one in Norway. And the thing is, we built ours real fast. And there's 2 reasons why we were able to build this robot so quickly. I can't see hands that clearly, but does anyone know why we were able to build this robot so fast? Anyone? on the Rachel Burson camera want to blurt out a reason as to why? Maybe you're on mute, so you can't say. Well, there's two reasons why. The first one is our staff and students are just amazing. There's nothing like it in the world, Carnegie Mellon. The other reason why is that when you saw our snake robots in the earlier video, you noticed they were modular. And it was our commitment to modularity that allowed us to build this robot fast. Because in the end, all we had to do was build 2 more modules. And then putting the robot together, I wouldn't say it's like putting Lego together, but the analogy is not a bad one. We figured out a lot of the systems problems in advance. I don't want to leave you with the impression that we're done. That robot is moving in clear water. Someone's watching it as it controls. There's a lot of work to be done there. So I want to change subjects to manufacturing for a moment, but space is going to be the theme here. And one of the things that it's of interest to me is developing both technology as well as curriculum for workers in robotics. And we want to make American workers so productive with our technology that we can compete with low cost laborers at other places. We also want to create jobs. We also want to make it easier for small companies to adopt robotic technology. Right now, you need an expert. And then finally, we want to assert American leadership. Now this doesn't mean, we're America, we should be in charge. No. What we want to do is we want to be reasonable collaborators and competitors with our peers in Europe and Asia. One fun fact is there are no manufacturers of industrial robots in the United States. There's no American company that makes industrial robots. And that's bad. We are the United States. We should be a leader, not a total follower. So with that in mind, we're bringing manufacturing into space. I just got this award called the Space University Research Initiative. And essentially, what we're doing is starting at the bottom, is we're going to do inspection, maintenance, and actually build structures in space. So let's talk about maintenance. This number always surprised me. There are about 6,300 satellites orbiting the Earth right now. And I thought there'd be more, but 6,300, and only half of them work. Most of them, they didn't break because they were faulty. They just ran out of time. They ran out of gas. They weren't supposed to last that long. So what we want to do is we want to build some mechanisms that will go into space and sort of revitalize dead satellites. So the way we're going to do that now is we have, let's say this is the broken satellite, the client vehicle, and our colleagues at Northrop Grumman have built this system here called the Mission Robotic Vehicle. And what it does is you launch into space, and then on board this vehicle, you have these pods called mission extension pods. And the vehicle has a bunch of these pods. Robot goes into space, gets to a client vehicle, takes a pod out of its back, and inserts it onto the dead satellite. And when you do that, what you end up with is, so what you're seeing moving there is an arm, peg in hole operation. Now this may seem easy to you. Many of us have keys that lock our doors. So when you stick a key into a lock, you're really doing a lot of really amazing things. You're watching, you're feeling your way in, and then it slides in perfectly. The tolerance that you have with that lock and key, it's just incredible that we maybe built them, and let alone we can control our hands to put a key in a lock. So imagine doing that in space, where everything is floating around. So if you hit the hole just a little bit off, you push that satellite off forever. And keep in mind, everything is moving at the same time. So not only you can put the peg in the hole, you got to put the moving peg in the moving hole. And that's the problem that we're solving right now on this project. Once we succeed in doing this, then we'll be able to revitalize satellites. You know, the name of our project is Break the Launch Once, Use Once paradigm. I think a lot of you may have heard of the James Webb Telescope. Right now, nobody knows how we're going to fill it up with gas in 10 years when it runs out of fuel. And I'm hoping that we'll be able to do that. Any questions? Okay, I'll go to the next slide. So this is a hard thing to do, and you just can't do it in simulation. You know, you want to do it on a real robot. But right now, we don't have the robot, you know, in space, in our lab. But some of the things we're doing is simulating what a floating robot may look like. So here we have these two robot arms, and the arm on the left is going to sort of move around in reaction to how the arm on the right, the one with the peg, hits the nozzle. So we're sort of simulating a free-floating environment with a robot arm. So the arm on the right is the same insertion robot. The arm on the left is the client vehicle, the satellite, and we're mimicking it being in space. And so far, the arm on the right isn't touching anything. And then finally, at the very, very end, it hits the choke point, and it actually causes the robot on the left to move. We're also coming up with new ways to simulate contact. When we touch something, we contact something, it's pretty great that we can sense it as well as understand it. And we're trying to develop new, new sensors for that as well. Okay, so what I want to do is I want to remind you that we're interested in manufacturing. That's that Robotics Institute, Advanced Robotics Institute we talked about. And one of the manufacturing projects we have is building airplanes without fixtures. See, when you build an airplane like a 737, it takes 9 years to place the order and for the plane to be built. And one of the reasons is when you assemble a plane, you have these large fixtures, these jigs to hold everything in place just precisely, so you can line up the holes perfectly. And that's necessary because it's an airplane. The problem is those fixtures are so big and they're expensive and they're time consuming to assemble. So what we want to do is get around the problem of these fixtures by building mobile robots. So we conceived of these designs that can then actually go and build the airplane wing without any fixtures. So here you're seeing an animation of robots assembling an airplane. There, one robot's carrying a rib, it's going to a spar. And we've been able to assemble ribs on spars already, but what we've done, I gotta be honest with you, it's really slow. So we still have a lot of work to do. There, the robots are carrying the skin that'll go underneath the spar, the wing ladder. So one of the challenges in not only conceiving of the design as well as describing the process is the planning for all of these robots. If you plan a path for one robot, that's a hard problem. If you plan a path for two robots, say this blue and gold robot, the problem, twice as hard. 3 robots is 4 times as hard. 4 robots is 8 times as hard. It grows exponentially. This is the curse of dimensionality. And one of the things we worry about in my group is reducing high dimensional problems to those that are tractable. And, with the snake robots, we do that as well. You have all these joints. How do you make it feel like you're controlling 2 things? So we developed these algorithms to do path planning for these robots. And what you have in the left corner, left side of the screen, is 200 paths being planned in real time with optimal guarantees, where there is not enough computation on the planet to compute those paths if you use standard approaches. So our approach does something, in the blink of an eye, that all the computers in the world using standard methods would have failed. And you can see on the right that now we're applying this to carrying, structures around, for building things, building those airplane wings. What we want to do, of course, is apply those ideas into space, to build structures in space. So since I mentioned something about multi-agent planning, I also want to point out that search and rescue, as I already alluded to, is an important task for me. And I want to tie the search and rescue and the multi-agent problem together. So here's, again, a problem that there's been a massive flood. And the thing you got to do is find the signs of life. And you got to do that as quickly as possible. Now, of course, it makes sense to get a bunch of drones and ground vehicles to drive. But again, where do you direct them? I already spoke about that curse of dimensionality. That problem with coordinating all your assets. But the other thing is, how do you know where to send your agents? So what we do is we have this thing called ergodic search. This map over here on the left, blue is where we think targets might be located, and gold is, yep, we know for a fact there are targets there. We're going to look there. And you don't want to concentrate all your robots where things are most likely to be, because your information could be wrong. So you want to balance out your search where you spend most of your time at the high likelihood locations and less time at the less likelihood locations. But you may discover in the low likelihood locations there are targets. So this is the so-called balancing exploration with exploitation. So when you're all said and done, you now have these approaches where you can go search with, and I might add, heterogeneous vehicles. Here you're flying overhead, and the bottom are ground vehicles looking for stuff, or looking for people, trapped survivors, and doing this in an optimal, time efficient way, because you want to locate survivors as quickly as possible. So I'm going to stop there. We worked on a ventilator. I'm going to stop there and have this as my closing slide, because it sort of summarizes some of the projects we discussed. And at this point, I'd like to take some questions. I see there's some questions in the chat, so I will look over at the chat now. Oh, that's cool. Another snake robot person. That's great. Wouldn't the point of contact to the fuselage? I wasn't sure what you meant by the point of contact, but the fuselage, ultimately, we put the plane together the way it is, but we would change the process by which the plane is put together because we're using robots. So in terms of search and rescue, you don't want the robots to change the environment. You want to keep the environment as still as possible, because it's already fragile and you don't want to cause any more additional disturbances. And I think that was, and I got a thumbs up to that. When dealing with, we need to take into account the contact dynamics of every manipulator while controlling arm. So you hit the nail on the head there. What we've done is our simulator, in which we're developing our system, is going to use contact that we sense from the two robots in our lab. So in other words, modeling contact in simulation is very hard. People don't do it. We just don't know how to do it. But what we're doing is regardless of what the robot is, with our robots, we're noting the motion that the end effectors, the distal end of the robot, take, and the contact that occurs in the workspace. We measure the workspace contact, and we project that back onto the simulated robot. And this gives us the opportunity to try a variety of robots, because it's easy to vary your robots in simulation. In fact, that's something that's taken us a long time to convince our partners is important.
So we have some questions here in the room. We would like to invite our students to come up ahead and ask themselves questions.
Oh, please.
Hello. I just have a question about the satellite rescue operations. And you showed the probe entering an interface on the satellite to attach your mission extension module. I'm just wondering, what do you do if satellites don't have that specific interface or weren't designed with that interface in mind? Do you have
Yeah,
other
yeah.
methods? Yeah.
So it turns out that the interface, it's the exhaust nozzle of the satellite.
Oh, okay.
And every satellite has an exhaust nozzle.
Okay. That makes sense.
Yeah. I had the same question too at first as well.
Okay. Thank you.
Yeah, thanks.
Hi, my name's Kylie. I was wondering about your snake robots. How compliant are they? Because the modules appear somewhat rigid, but they're also look like they have compliant joints. So I was wondering how much compliance they had.
Okay, I suspect your question is a veiled question about soft robots. Is that right?
Yes.
Okay. So compliance means, as the name suggests, is how the robot can comply and adhere to changes in the environment. Okay. And the snake robots you saw definitely appear to be rigid links. Now, the reality is we can bend our joints every which possible way. We can always comply to the environment, and we spend a fair bit of time doing that. But that's hard. So one of the things we've done, and that's what's in these robots, is these joints are called series elastic actuators. So series means in a row, elastic like a spring, and then an actuator, motor. Series elastic actuator. S-E-A. And a series elastic actuator is one where you have a motor that spins. At the output of a motor is a torsional spring, and then output of that is, and then the output of that is the system. So if there's no load on the system, everyone spins together. And if there is some sort of load on the system, there's a deflection. Now, because we have this deflection, we can back out the torque or force, Hooke's law, that the joint is experiencing. So we're able to close the loop on force. So now we can tell the robot at the joints, we can literally modulate, program in the stiffness we care for the joints to have. So it is the case that there is a spring of something soft inside there that allows the material, the robot to comply, as well as give us the information is by how much it is complying. One fun fact is, if you look at the robot in the upper left corner of the screen, that's a medical snake robot that we used for minimally invasive surgery, which everyone called rigid. It has 102 links, and there's cables going through it, only 4, that marionette the position shape of the robot. But the truth is, when we're in the heart or the outside of the heart, driving around the heart, we just loosen the joints a little bit, and then we just tell the robot go straight, and it naturally contours to the shape of the heart. Because it's rigid in the right direction going forward, and it's compliant in the orthogonal direction. Yeah, there were a lot of people who said you need to have soft robots for surgery, and maybe it's rude of me to say they're all wrong, but I can say none of them have ever made it into surgery yet, and they've been saying this for at least 20 years now. Like even my robot, that one on the left, it's operated on 1,500 people already.
Yeah, that was really interesting. Thank you.
Thank you.
Hi, I was wondering, in terms of some of the applications you mentioned, like assembling airplanes and whatnot, why use something like multi-agent planning instead of maybe a more from scratch approach like multi-agent reinforcement learning? Is planning just like leagues ahead still?
Okay, so the question that was asked is, why use planning approaches when you can just go use multi-agent reinforcement learning? Now, for one thing, I think that all too often people jump to reinforcement learning before trying classical techniques. And it's pretty amazing as to how far we've gotten with just conventional planning approaches. Now, with that in mind, we are doing research on multi-agent reinforcement learning. And believe it or not, the problem with multi-agent reinforcement learning, just like with planning, is the curse of dimensionality, how well you scale as the number of agents increases. And our approach pretty much uses a combination of reinforcement learning and imitation learning, where the experts are our algorithms that we developed in the first place to guide the reinforcement learning. So I advocate, start with the simple conventional approaches first and prove that you need to jump to something additional like reinforcement learning, or at the very, very least, if you're going to implement something straight up in reinforcement learning, be aware that people have implemented stuff before without it. I would say, 99 times out of 100, when a student comes to me saying, oh, I'm working on this approach, I think I'm going to use reinforcement learning, they never exceed the capability of what a conventional approach has done.
I see. Thanks.
And thank you.
Hello, I have a question.
I'm sorry, once again. So for multi-agent planning, there's so much work to be done, especially when it comes to heterogeneous agents, having agents of different types working together, cooperating. Multi-objective, multi-agent planning, we have multiple criteria you want to deal with. Being able to handle communication loss in multi-agent planning. Oh, there's so much. I'm sorry, go on.
Hi, I have a question about your manufacturing robots. So they kind of like working in a team and they're kind of like independent, but is there a situation where one robot like accidentally breaks apart? Is it able to like recognize that and then realize that you need to fix something, like get a new part or something like that?
So those aren't my robots, those are industrial robots.
Oh.
And they are, like you said, working individually in a sequence. So when, let's just use your iPhone, for example. So when this iPhone's being built, I forget the number, but there's about 230 operations that go into the iPhone construction, and about 150 of them, significantly more than half are inspection. So in other words, yeah, you're whipping along building your phone, but you're more often making sure whatever you just did works, or did the right thing, or whatever the robot just did. So yeah, they definitely do lots and lots of inspection as they automate.
Cool. Thank you.
Thank you.
Hi, just a quick question. You said you had with the multi-agent planning robots, you said there was like when it comes to more robots, the power grows exponentially, right? So how were you able to exceed the need for power? Like you said earlier.
So the problem grows exponentially, and the reason why is when you have two robots, you have to coordinate two guys. 3 robots, you have to coordinate all 3 at the same time. 4, imagine you're on a checkerboard or on a grid. 1 robot goes up, down, left, right. 2 robots, you have up, 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 left, up, down, up, right, up, left, up. Then you have left, left, up, left, left. You have all these combinations, and you can imagine as you have 3, 4. The number of combinations just grows exponentially. What we've done is we recognize that all robots don't have to be coordinated at the same time. And by bounding the set of robots that need to be coordinated, you can bypass that curse of dimensionality.
Okay. And one more question, right? You also did say that there are no robotics companies in America. Isn't NREC a robotic company?
So first, let me be clear. What I said is there's no company in the United States making industrial robots.
Oh, okay.
And NREC is a center that's part of the Robotics Institute.
Right.
It's not a company. Pittsburgh has the most number of robotics startups created each year than any other city in the world. We've tons of companies, but none of them are working on industrial robots, and none of them are big.
Thank you.
Thank you.
I also have another question.
Sure.
What would be like the differentiative factor of the snake robots during the search and rescue projects, such like an earthquake situation that you described earlier?
When you say the differentiating factor, differentiating from what?
From other bigger robots that have been like designed for that similar purpose.
So I'm not aware of any robot that's been specifically designed for search and rescue, for one thing, but they've used some robots which were generally designed to crawl in pipes. But the big difference is the snake robot has a smaller cross-sectional diameter, so it can go through tighter holes, and it can go this way, up, left, right, all possible different directions. But it's really getting into the tight spaces that makes the snake robot pretty great when compared to other robots.
And how fast is that you can get the robot to the place of that natural disaster? Of how fast is the response towards that?
So do you mean from the point in time we're asked to go to deployment, or once we're deployed?
For deployment.
I think for Mexico City, it was 48 hours.
Okay,
No,
thank you.
We're pretty portable. Everything we have and we bring with us is it goes in the overhead compartment on the airplanes. We don't check our luggage, so we're pretty quick.
That's good. I think.
No,
I had
that's it.
a
Oh, please.
Thanks. I was wondering how you became like interested in like the field you talked about, or like what got you interested in robotics?
Ever since I was a small child, I always found motion, like my hands moving around, cars driving, the way animals move. I always found motion to be interesting. And I was always mesmerized by how we coordinate our motion, whether it's from our own joints, muscles, or traffic signals that tell us which way to go. I just find all kinds of motion to be interesting. And it's not just say where to go, it's also closing the loop, based on what sensors you have, where to go as well. So, but it all comes down to motion.
Thank you.
Yeah, thank you.
Are there any final questions in the room? Okay. Well, I think those are all the questions. Thank you so much for your time.
No, thank you for your time, and best of luck. Have a good rest of summer.